Imagine a world where a full day lasts less than the time it takes to watch a movie. A world spinning so quickly that gravity itself struggles to keep it together. Most planets in our solar system rotate calmly, taking many hours or even days to complete a single turn. But one distant object refuses to follow the rules. It spins faster than almost anything its size should be able to survive. So fast, in fact, that the planet itself has been stretched into an oval shape, as if centrifugal force is pulling it apart. This strange, elongated world is called Haumea. At first glance, it might look like just another frozen body drifting quietly in space. But Haumea is anything but ordinary. It rotates once every 4 hours, the fastest known rotation of any large planetary object in the solar system. That speed is so extreme that the planet is no longer round. Instead, it has been distorted into something closer to a cosmic egg. Even stranger, Haumea is surrounded by a thin ring of icy debris and 2 small moons that may have formed after a catastrophic collision billions of years ago. In other words, this world may once have been shattered. Tonight, we're going to explore one of the most unusual objects ever discovered in our solar system, a spinning world of ice, a planetary survivor of an ancient cosmic crash, and perhaps the fastest rotating planet-like body we've ever found. This is the story of Haumea. And once you understand how fast this world spins, you may start to wonder how it hasn't torn itself apart. In the early 2000s, astronomers scanning the outer edges of the solar system were not expecting to find something truly bizarre. By that time, scientists had already discovered several objects beyond Neptune. These distant bodies, scattered across the Kuiper Belt, were usually small, dim, and extremely cold. Most of them looked fairly ordinary, frozen remnants left behind from the chaotic era when the planets first formed. But occasionally, one of those faint moving dots on a telescope image turns out to be something extraordinary. That is exactly what happened with Haumea. The story begins in December 2004, when astronomers using the Palomar Observatory in California were carefully analyzing images of the night sky. The telescope had captured thousands of stars and distant objects. Most of them were stationary points of light, but astronomers were searching for something different, objects that slowly moved across the background stars over time. Movement in the sky often reveals a nearby body in our own solar system. And eventually, one faint object did exactly that. At first glance, it looked like just another Kuiper Belt object. But when astronomers began studying it more closely, strange details started to appear. The object was brighter than expected. It also seemed to rotate incredibly quickly. Over the following months, researchers began tracking the object's brightness carefully. As it rotated, the amount of light reflecting toward Earth changed dramatically. The brightness would rise, then fall, then rise again. At first, this might not sound unusual. Many asteroids and dwarf planets show slight brightness variations as they rotate. But the variation seen here was extreme. It was as if the object had a very unusual shape. Then came the most surprising discovery of all. By measuring the timing of those brightness changes, astronomers realized the object completed one full rotation in just 4 hours. That is astonishingly fast for a body of its size. For comparison, Earth takes 24 hours to rotate once. Even Jupiter, the fastest spinning planet, takes about 10 hours. But this distant icy world was spinning more than twice as fast as Jupiter. For an object hundreds of kilometers across, that kind of speed should be almost impossible. If a large celestial body spins too quickly, centrifugal force begins to overcome gravity. Eventually, the object can no longer hold itself together. It starts to stretch, and if the rotation becomes too extreme, the object can even break apart. So how was this distant world surviving such a rapid spin? The answer turned out to be just as strange as the rotation itself. Further observations revealed that Haumea was not spherical like most planets or dwarf planets. Instead, it had been stretched into an elongated shape. Rather than looking like a ball, Haumea resembles something closer to an oval, or even a slightly flattened football. This unusual shape is the direct result of its extreme rotation. As the object spins, centrifugal force pulls material outward along its equator. Over time, that force has distorted the entire body. In fact, Haumea is one of the most dramatically shaped large objects ever discovered in our solar system. But the mysteries did not stop there. As astronomers continued studying Haumea, they discovered that it was not alone. Orbiting around it were two small moons. The first moon, named Hiʻiaka, is the larger of the two. It orbits Haumea at a considerable distance. The second moon, Namaka, follows a closer and slightly more chaotic orbit. The presence of these moons added another important clue to the story. Moons often form after large collisions. For example, many scientists believe our own moon formed after a Mars-sized body collided with the early Earth billions of years ago. Could something similar have happened here? The evidence began to point in that direction. Around the same time Haumea was discovered, astronomers noticed a small group of other icy objects in the Kuiper Belt that seemed strangely related. These bodies shared similar orbital paths. Even more interesting, they also appeared to be composed largely of water ice, a composition that closely matched Haumea's surface. It was as if they were fragments from the same original object. This group of bodies eventually became known as the Haumea family, and many astronomers now believe they were created during a colossal impact event billions of years ago. Imagine a young solar system, still filled with debris and unstable orbits. Two large icy worlds collide at tremendous speed. The impact shatters one of them. Huge pieces of ice and rock are thrown into space. Some fragments escape entirely. Others remain nearby, eventually forming moons. And the surviving core of the shattered world continues spinning faster and faster after the collision. That surviving core may be the object we now call Haumea. If this theory is correct, Haumea is not just a strange planet. It is a planetary survivor, a world that endured one of the most violent collisions in the history of the solar system. Over time, its rapid spin stretched it into the elongated shape we see today. Its moons formed from the debris of that ancient catastrophe, and the scattered fragments of that collision still drift through the Kuiper Belt. But one more surprising discovery was waiting. In 2017, astronomers made another unexpected observation. Using a technique called stellar occultation, watching what happens when a distant object passes in front of a star, scientists were able to study Haumea with remarkable precision. As the dwarf planet moved across the sky, it briefly blocked the light of a distant star. By measuring how that starlight disappeared and reappeared, researchers could map the shape and surroundings of Haumea. What they found was astonishing. Haumea appeared to have a ring. Rings are usually associated with giant planets like Saturn. But Haumea is only a dwarf planet, far smaller than any of the gas giants. And yet somehow, it possessed its own thin ring of icy debris orbiting around it. This discovery made Haumea even more unusual. Not only was it the fastest spinning large object in the solar system, not only did it have an elongated shape and 2 moons, it also had a ring system, something almost no dwarf planet possesses. All of these clues point toward a dramatic past, a past shaped by collision, rotation, and gravitational chaos. And yet, despite everything that happened, Haumea still exists today, racing around the sun once every 285 years, spinning faster than any planet-like body should. But this raises an important question. How fast can a world spin before it finally breaks apart? In the next part, we will explore the incredible physics behind Haumea's rotation and why scientists believe this strange world may be spinning right at the very edge of destruction. Far beyond the orbit of Neptune, where sunlight is weak and temperatures fall hundreds of degrees below freezing, the dwarf planet Haumea continues a silent and relentless spin. Every 4 hours, it completes another rotation. 4 hours. For a body nearly 2,000 kilometers across, that is an extraordinary speed. To understand just how extreme this is, imagine standing on the surface of such a world. The ground beneath you would be racing sideways at enormous velocity, pulled outward by centrifugal force. The faster an object spins, the stronger that outward force becomes. Normally, gravity holds a planet together. Gravity pulls all material toward the center, keeping the body round and stable. But when rotation becomes too fast, a competition begins. Gravity pulls inward. Rotation pushes outward. And if the outward force becomes too strong, the object begins to deform. That is exactly what happened to Haumea. Instead of forming a sphere like Earth, Haumea has been stretched into what scientists call a triaxial ellipsoid. This means the planet has 3 different axes of length, almost like a slightly squashed rugby ball or a stretched egg. Its longest dimension is roughly 2,300 kilometers, while the shorter dimensions are much smaller. That distortion is not random. It is the direct result of its incredible rotation. When a celestial body spins quickly, material near the equator experiences stronger outward force than material near the poles. Over millions of years, this causes the equator to bulge outward, while the poles flatten. On Earth, this effect exists too, but it is subtle. Our planet is slightly wider at the equator than from pole to pole. But on Haumea, the effect has become extreme. Its entire structure has been reshaped by rotation. In fact, Haumea is so distorted that if you could see it up close, it might not even look like a typical planet at all. Instead, it would resemble a rapidly spinning cosmic rock stretched sideways by its own motion. And yet, despite spinning so quickly, Haumea has not torn itself apart. Why? To answer that question, scientists had to study the internal structure of the dwarf planet. Observations suggest that Haumea is made mostly of rock and ice. but not evenly mixed. The interior is thought to contain a dense rocky core surrounded by a thick mantle of water ice. That icy outer layer reflects a large amount of sunlight, which is why Haumea appears unusually bright compared to many other objects in the Kuiper Belt. But this icy mantle also raises another interesting question. Water ice is not as strong as rock. Under enough stress, ice can fracture or deform. So how has Haumea's icy surface survived billions of years of rapid spinning? One possible answer lies in its violent past. Many scientists believe Haumea experienced a massive collision long ago. That collision may have stripped away much of its outer layers, leaving behind a dense, rapidly rotating core. The debris from that impact likely formed the group of icy objects known as the Haumea family, and the remaining body, the object we see today, continued spinning faster and faster after the collision, conserving angular momentum. Imagine a figure skater spinning on ice. When the skater pulls their arms inward, they spin faster. The same principle applies in space. If a planet loses mass during a collision, the remaining material can spin more quickly. Haumea may be the result of exactly that process. A shattered world spinning faster after its ancient impact. But even with that explanation, the physics is still extraordinary. There is a limit to how fast any celestial body can rotate before gravity can no longer hold it together. This limit is known as the breakup speed. If Haumea was spinning much faster than it already is, centrifugal forces would begin to overcome gravity entirely. At that point, pieces of the surface could break free and drift into space, and eventually, the entire object might begin to disintegrate. In other words, Haumea may already be spinning close to the maximum speed that a body of its size can survive. This raises a fascinating possibility. Perhaps Haumea is balanced right on the edge of destruction. Over billions of years, its rotation may have slowly decreased as tiny particles escaped from its surface. Or perhaps the planet reached a stable equilibrium, a delicate balance between gravity and rotation that has persisted for eons. But Haumea's rotation does more than reshape the planet itself. It also affects the way the dwarf planet interacts with its surroundings. For example, the ring discovered around Haumea in 2017 may be directly related to its rapid spin. When astronomers studied how the dwarf planet passed in front of a distant star, they noticed something unusual. Before the star disappeared behind Haumea, its light dimmed slightly. Then, after Haumea passed, the same dimming occurred again. This symmetrical pattern suggested that something thin and circular was orbiting the planet. Further analysis confirmed the presence of a narrow ring. This ring lies about 2,300 kilometers from the center of Haumea, remarkably close to the dwarf planet's equator. And interestingly, the ring orbits at almost exactly the same period as Haumea's rotation. That may not be a coincidence. Some researchers believe that particles thrown off the planet's equator, perhaps due to its rapid spin, may have gradually formed the ring we observe today. If so, Haumea could be slowly shedding material into space, tiny fragments escaping its surface and joining the thin disk of icy debris circling the planet. Over immense periods of time, that process could subtly reshape the entire system. But the mysteries of Haumea extend beyond its rotation and rings. its surface itself appears unusual. Spectroscopic observations show that Haumea's surface is dominated by crystalline water ice, a form of ice that typically requires some heating to form. That is surprising. The Kuiper Belt is incredibly cold, often colder than -220 degrees Celsius. Under such conditions, crystalline ice should gradually transform into a more disordered structure called amorphous ice. Yet Haumea's surface remains crystalline. This suggests that something has heated the surface at some point in the past. One possibility is that the ancient collision that created Haumea also melted parts of its surface. Another possibility is that internal heat from radioactive elements deep inside the rocky core could slowly warm the interior. That heat might occasionally reach the surface through fractures or cryovolcanic activity. If that happened, Haumea might once have experienced icy eruptions, jets of water and ice bursting from its surface before freezing instantly in the vacuum of space. Even today, scientists are not entirely sure. The dwarf planet remains distant and difficult to observe, more than 6 billion kilometers from the Sun. At that distance, Haumea appears as little more than a faint point of light in even the most powerful telescopes. Yet from that tiny dot, astronomers have already uncovered one of the most unusual worlds in the solar system, a planet stretched by its own rotation, surrounded by a ring, accompanied by 2 moons, and possibly formed from the debris of a catastrophic collision billions of years ago. But the real mystery may be even deeper, because if Haumea truly formed from a violent impact, then the dwarf planet we see today may only be the surviving core of something much larger, a remnant of a world that once existed long before the solar system settled into the orderly structure we see today. In the next part, we will explore that ancient collision in more detail. What kind of impact could shatter a planet and leave behind a spinning survivor like Haumea? And what clues still remain scattered across the Kuiper Belt, revealing the aftermath of one of the solar system's most dramatic events? Long before astronomers ever pointed their telescopes toward Haumea, something extraordinary happened in the distant outskirts of our solar system. An event so violent that it reshaped an entire world. To understand Haumea today, its rapid rotation, its strange elongated shape, its ring, and even its moons, scientists believe we must travel billions of years into the past, back to a time when the outer solar system was far more chaotic than it is now. In those early days, the region we now call the Kuiper Belt was crowded with countless icy worlds. Some were small, only a few kilometers across. Others were enormous, large enough to become dwarf planets. But unlike the relatively stable environment we see today, these objects were constantly interacting. Their orbits crossed, their gravitational fields tugged on one another, and occasionally they collided. Not gentle impacts, but catastrophic ones. One of those impacts may have created the world we now know as Haumea. Astronomers began suspecting this when they noticed something unusual while studying objects in the Kuiper Belt. Several distant bodies shared remarkably similar orbital paths. At first glance, this might not seem strange. After all, many objects orbit the Sun in roughly the same region. But when scientists analyzed the light reflecting from these objects, something remarkable appeared. They all had very similar surface compositions. Each one was covered in nearly pure water ice. That was highly unusual. Most Kuiper Belt objects contain a mixture of darker materials, organic compounds, methane ice, nitrogen ice, and other frozen chemicals. But these objects were different, bright, reflective, and dominated by crystalline water ice. Even more intriguing, their orbits suggested they once originated from the same location, almost like fragments from a shattered body. This group of objects became known as the Haumea family, and their existence strongly suggested that a massive collision once took place. Imagine a large icy world drifting quietly in the outer solar system billions of years ago. This original planet may have been significantly larger than Haumea is today. Then, at some point, another large object crossed its path. The two bodies approached each other at incredible speeds, several kilometers per second. In space, even a small object moving that fast carries enormous energy. But these were not small objects. These were planetary bodies. When they collided, the impact would have released an almost unimaginable amount of energy. The outer layers of the planet would have been blasted away instantly. Chunks of ice and rock would have been hurled into space in every direction. Some fragments would escape entirely, becoming independent objects orbiting the Sun. Others would remain gravitationally bound to the surviving core. Over time, those fragments might clump together, forming moons. And the central remnant, the core that survived the collision, would continue spinning. But something else would happen during such a catastrophic event. The rotation of the planet could dramatically increase. The physics behind this is related to angular momentum. When a body loses mass during a collision, the remaining material can spin faster, much like a spinning skater pulling their arms inward. In Haumea's case, the impact may have stripped away a large portion of its outer layers. The surviving core then began rotating faster and faster, until eventually it reached the extreme speed we observe today. This theory explains several mysteries at once. It explains why Haumea rotates so quickly. It explains why its shape is elongated rather than spherical. And it explains why a family of icy fragments exists nearby. But perhaps the most fascinating evidence of this ancient collision lies in Haumea's moons. Two small satellites orbit the dwarf planet today. They are called Hiʻiaka and Namaka. These moons are not large. Hiʻiaka is roughly 310 kilometers across. Namaka is much smaller, about 170 kilometers wide. Yet their composition tells an important story. Like the Haumea family objects, both moons appear to be composed mostly of water ice. That strongly suggests they formed from the debris of the same ancient collision. Fragments that never escaped Haumea's gravity. Instead, they slowly gathered together, forming two small moons that still orbit the dwarf planet today. The outer moon, Hiʻiaka, travels much farther from Haumea and takes about 49 days to complete an orbit. Namaka orbits closer and moves faster, but their orbits are not perfectly stable. Gravitational interactions between the moons and Haumea create subtle changes in their motion. These interactions have allowed scientists to calculate Haumea's mass with surprising accuracy. Despite its large size, Haumea is actually less massive than many other dwarf planets. This again supports the idea that it lost a large amount of material during the ancient collision. In other words, Haumea may be the surviving core of a once larger world, but the collision did more than create moons. It may also explain the strange ring discovered around Haumea. Rings are common around giant planets like Saturn, but they are extremely rare around small bodies. Before Haumea's ring was discovered in 2017, astronomers had only found rings around a few other minor bodies. Yet Haumea's rapid rotation makes such a structure possible. When debris from the ancient collisions spread outward, some fragments may have settled into stable orbits around the dwarf planet. Over billions of years, those particles could gradually form a thin ring, a fragile halo of icy fragments circling the spinning world. The ring lies very close to Haumea's equator, a region where the planet's rapid rotation has the greatest effect. Particles there experience strong centrifugal forces. If fragments drift too close to the surface, they might be pulled apart or launched back into orbit. But at just the right distance, they can remain suspended, endlessly circling the dwarf planet. This delicate balance between gravity and rotation may explain why the ring has survived for so long. But the story of Haumea's collision may reach even further than its moons and ring. Some scientists believe the impact may have reshaped an entire region of the Kuiper Belt. The fragments that escaped Haumea's gravity could have spread across millions of kilometers of space, each piece continuing its own independent orbit around the Sun. Today, those fragments still exist, small icy worlds drifting silently through the darkness, and when astronomers study them, they see echoes of that ancient collision. The same reflective surfaces, the same water-ice signatures, the same orbital patterns. Together, they form a kind of cosmic family tree, a scattered record of a single violent event that occurred billions of years ago. But one question still remains. If Haumea truly formed from such a catastrophic collision, why did the central body survive at all? Why wasn't the entire planet destroyed? The answer may lie in the nature of the impact itself. Not all planetary collisions are direct head-on crashes. Some are glancing blows. In these cases, the colliding body strikes at an angle, removing large amounts of material but leaving the central core mostly intact. This kind of impact could strip away Haumea's outer layers while allowing the inner core to survive. And if the impact occurred at just the right angle, it could also increase the planet's rotation dramatically. The result would be exactly what we observe today, a rapidly spinning remnant, surrounded by fragments of its own past, a survivor of a catastrophic event that reshaped its entire structure. In many ways, Haumea may be one of the most dramatic examples of planetary violence in our solar system, a world that was shattered but not destroyed. Instead, it continued spinning through the darkness for billions of years, a frozen relic of a long-forgotten collision. And even today, as telescopes grow more powerful and observations become more precise, scientists are still uncovering new clues about this strange and distant dwarf planet. Because Haumea is not just another icy body at the edge of the solar system. It is a survivor, a planetary fragment that endured one of the most violent events in the history of the outer solar system. And yet, the deeper astronomers look, the more questions emerge. For example, Haumea's surface is unusually bright, much brighter than most objects in the Kuiper Belt. Why? Is the surface being refreshed somehow? Are internal processes still active beneath the frozen crust? Or are we seeing the exposed layers of the planet's interior revealed during the ancient collision itself? Those questions remain unanswered, but they hint at something fascinating. Haumea may not simply be a relic of the past. It may still be evolving, still changing, still revealing new secrets about how planets form, collide, and survive in the most distant regions of our solar system. And as we continue exploring the Kuiper Belt, worlds like Haumea remind us that even in the coldest, darkest parts of space, the history of our solar system is far more violent than it first appears. In the solar system, most worlds follow a familiar rule. If a celestial body becomes large enough, gravity pulls it into a sphere. This happens because gravity acts equally in all directions, slowly smoothing mountains, valleys, and irregular shapes over immense periods of time. Eventually, the body settles into the most stable form possible, a sphere. This is why planets like Earth, Mars, and even the dwarf planet Pluto appear round when viewed from space. But Haumea does not follow that rule. Instead of being spherical, Haumea has one of the strangest shapes of any known planetary body. It is stretched, distorted, and permanently deformed by its incredible rotation. Scientists describe Haumea as a triaxial ellipsoid. That means its three axes all have different lengths. Rather than being shaped like a ball, Haumea resembles something closer to a flattened oval or an elongated rugby ball. Its longest dimension measures roughly 2,300 kilometers, while the other dimensions are significantly smaller. If you could see Haumea from a distance, it would not look like a typical planet at all. Instead, it would appear as a rapidly spinning icy body with a noticeably stretched silhouette. This shape is not random. It is the direct result of its extraordinary rotation. Haumea completes one full spin every 4 hours. That speed generates powerful centrifugal forces that push material outward along the planet's equator. Over billions of years, this force has gradually reshaped the entire body. Material near the equator has been pulled outward. Meanwhile, the polar regions remain more compressed. The result is a planet that has been physically stretched by its own motion. On Earth, something similar happens, but on a much smaller scale. Our planet is slightly wider at the equator than at the poles. The difference is only about 43 kilometers, so it is barely noticeable. But Haumea takes this effect to an entirely different level. Its extreme rotation has amplified the equatorial bulge dramatically, transforming the entire planet. In fact, Haumea may be the most dramatically distorted large object in the solar system. And that raises a fascinating question. Why hasn't it broken apart? When an object spins too fast, centrifugal force begins to overpower gravity. If the rotation becomes extreme enough, pieces of the surface could escape into space. Eventually, the entire object might begin to fragment. Yet Haumea has remained intact for billions of years. The key lies in the balance between rotation and gravity. Even though Haumea spins incredibly fast, it still possesses enough mass to hold itself together. Its gravity continues pulling material inward, resisting the outward push of rotation. This delicate balance creates a stable but unusual structure. Haumea exists in a kind of equilibrium, a cosmic tug-of-war between gravity and motion. But Haumea's unusual shape creates another interesting effect. Because the planet is elongated, the amount of sunlight it reflects toward Earth changes dramatically as it rotates. Imagine observing a spinning football from far away. When the long side faces you, it reflects more light. When the narrow end faces you, less light is reflected. This variation in brightness is exactly how astronomers first realized that Haumea had such an unusual shape. As it rotates, its brightness rises and falls in a predictable pattern. The difference is surprisingly large, far greater than what scientists see from most spherical bodies. By studying these brightness changes carefully, astronomers were able to estimate Haumea's dimensions and rotation rate. Even though the dwarf planet is far too distant for most telescopes to resolve clearly, these subtle variations in light revealed the truth. Haumea was not round, it was stretched. And that discovery confirmed just how extreme the planet's rotation really is. But Haumea's shape may also tell us something about its internal structure. Most models suggest that the dwarf planet contains a dense, rocky core surrounded by a thick mantle of water ice. The rocky interior provides the gravity needed to hold the planet together. Meanwhile, the icy outer layers are more flexible and able to deform under the stresses caused by rotation. This combination may allow Haumea to maintain its elongated shape without completely breaking apart. The ice slowly adjusts to the forces acting on it, redistributing mass over long timescales. In effect, Haumea's icy mantle behaves almost like a very slow-moving fluid. Over millions of years, it reshapes itself to match the balance between gravity and rotation. But Haumea's shape may also influence the behavior of its ring. The thin ring surrounding the dwarf planet lies very close to the equatorial region, the area most affected by centrifugal forces. Particles in the ring orbit at nearly the same rate that Haumea itself rotates. This creates a fascinating relationship between the planet and the ring. In some ways, the ring behaves like an extension of Haumea's equator, a cloud of icy debris suspended just beyond the planet's surface. Some scientists even suspect that the ring may have formed from material thrown off Haumea during its ancient collision or later rotational stresses. If fragments of ice were launched into orbit, they could gradually settle into the narrow ring observed today. But the ring itself remains fragile. Unlike the massive rings of Saturn, Haumea's ring is thin and faint. It contains far less material. And because Haumea's gravity is relatively weak, the ring may slowly evolve over time. Tiny particles could drift inward or outward under the influence of gravitational forces and radiation from the sun. Over millions or billions of years, the ring may eventually disperse. But for now, it remains a remarkable feature. A ring orbiting a rapidly spinning dwarf planet at the edge of the solar system. Another reminder that Haumea refuses to behave like a typical world. Yet the deeper astronomers study Haumea, the more mysteries emerge. For instance, its surface is extraordinarily bright. Haumea reflects a large percentage of the sunlight that reaches it, making it one of the most reflective objects in the Kuiper Belt. This suggests that its surface is covered in relatively clean water ice. But that presents a puzzle. In the harsh environment of the outer solar system, radiation from cosmic rays and solar particles should gradually darken the surface over time. Yet Haumea remains unusually bright. This implies that something may be refreshing the surface. Perhaps the ancient collision exposed fresh layers of ice, or maybe internal activity has occasionally resurfaced parts of the planet. Another possibility is that the rapid rotation itself causes small landslides or shifts in the icy crust. These processes could expose fresh ice beneath the surface, maintaining Haumea's bright appearance. But without a spacecraft mission to observe the dwarf planet up close, many of these questions remain unanswered. For now, Haumea remains a distant mystery, a world spinning through the darkness more than 6 billion kilometers from the Sun, a planet stretched by its own rotation, a survivor of a catastrophic collision, and perhaps one of the most physically extreme objects in the entire solar system. Yet despite everything astronomers have already discovered, Haumea may still hold deeper secrets, because its unusual shape and rotation hint at something even more extraordinary. A planetary body that may be spinning almost as fast as physics allows. A world balanced right at the edge of structural stability. And that raises one final question. If Haumea was spinning just a little faster, would it still exist today? Or would it begin to tear itself apart, scattering icy fragments into the Kuiper Belt and creating yet another family of cosmic debris? In the next part, we will explore the limits of planetary rotation itself. How fast can a world spin before gravity finally loses the battle? And how close might Haumea already be to that ultimate breaking point? Every object in the universe can spin. Asteroids tumble slowly through space. Planets rotate as they orbit their stars. Even entire galaxies slowly turn over billions of years. Rotation is one of the most fundamental motions in the cosmos. But there is a limit. No matter how large a planet is, it cannot spin forever faster and faster. Eventually, physics draws a line, a point where rotation becomes too extreme for gravity to hold the object together. Beyond that limit, the planet would begin to break apart. For most worlds in our solar system, this limit is never approached. Take Earth, for example. Our planet rotates once every 24 hours. At the equator, the ground beneath us is moving sideways at about 1,670 kilometers per hour. That might sound fast, but compared to the planet's gravity, it is relatively gentle. If Earth suddenly rotated twice as fast, the day would be only 12 hours long, yet the planet would still remain stable. But if Earth somehow rotated once every 2 or 3 hours, things would start to change dramatically. The outward force at the equator would increase enormously. Oceans would begin migrating toward the equator. The planet would bulge outward more dramatically. And if the rotation became fast enough, gravity might no longer be strong enough to hold the surface together. At that point, material could begin escaping into orbit. Earth would start to shed mass. Eventually, it could even form a ring. Fortunately for us, Earth rotates far below that dangerous threshold. But Haumea is a very different story. Haumea rotates once every 4 hours. For a planetary body roughly 1,600 kilometers across, that is extraordinarily fast. Scientists estimate that parts of Haumea's equator may be moving at more than 900 kilometers per hour relative to its center. That speed generates enormous centrifugal forces, and yet the dwarf planet still holds together. How? To answer that question, Astronomers use models that compare two competing forces. Gravity pulls everything toward the center of the planet. Centrifugal force pushes material outward as the planet spins. When these two forces are balanced, the object reaches a state of equilibrium. But if centrifugal force becomes stronger than gravity, the surface begins to destabilize. Material can lift away from the planet. In extreme cases, the object could even break apart completely. Scientists call this the critical rotation limit. It represents the maximum speed a planet can rotate before it begins losing mass. Interestingly, that limit depends heavily on the planet's density. A dense, rocky planet has stronger gravity and can spin faster without breaking apart. A low-density icy body, however, has weaker gravity and reaches its limit much sooner. Haumea falls into the second category. It is believed to be composed of a rocky core surrounded by a thick mantle of water ice. Because ice is less dense than rock, Haumea's gravity is weaker than that of similarly sized rocky planets. That means its rotational limit should be lower. And yet, Haumea spins extremely fast, close to the theoretical limit. In fact, some scientists believe Haumea may already be rotating near the maximum speed that physics allows for a body of its size and composition. If the planet was spinning only slightly faster, centrifugal forces might begin ejecting material from the equator. This idea becomes even more intriguing when we consider Haumea's ring. The ring discovered around the dwarf planet lies very close to the region where centrifugal forces are strongest. Some researchers believe the ring could be composed of particles that once belonged to Haumea itself. Fragments of ice that were launched into orbit as the planet spun near its stability limit. Over time, those fragments could settle into a narrow ring circling the equator. If this hypothesis is correct, Haumea may be slowly shedding material, not in dramatic explosions, but in subtle processes that occur over millions of years. Tiny fragments could escape the surface, gradually feeding the ring system. This would mean Haumea is not just spinning quickly. It may actually be evolving because of that rotation. But Haumea's rotation may also influence its internal structure. When a planet spins extremely fast, its interior experiences different pressures compared to a slowly rotating body. Material near the equator feels stronger outward forces. Meanwhile, material near the poles remains more compressed by gravity. This uneven distribution of forces can reshape the internal layers of the planet. Over long periods of time, the interior may rearrange itself to maintain stability. This process is known as hydrostatic adjustment. Essentially, the planet gradually shifts its mass until the internal stresses balance out. For Haumea, this adjustment likely helped create its elongated ellipsoidal shape. But the story might not end there. Some astronomers suspect that Haumea's rapid rotation could also affect its surface geology. Even though the dwarf planet is extremely cold, with temperatures around -220 degrees Celsius, the icy crust might still respond to stress. Ice can behave in surprising ways over long timescales. Under pressure, it can flow slowly, almost like a thick fluid. If Haumea's rotation is stretching the surface, the icy crust could gradually deform. Cracks might open along the equator. Large slabs of ice might shift or slide. And in rare cases, deeper layers of ice could rise to the surface. These processes might explain why Haumea appears unusually bright compared to many other Kuiper Belt objects. Fresh ice exposed by geological activity would reflect more sunlight than older, radiation-darkened surfaces. But because Haumea is so distant, more than 6 billion kilometers from the Sun, studying its surface directly is extremely difficult. Even the most powerful telescopes can only detect subtle variations in light. To truly understand Haumea's geology, we would need a spacecraft mission traveling deep into the outer solar system. Such a mission would take decades to reach its destination, yet the scientific rewards could be extraordinary. Haumea represents one of the most extreme natural experiments in planetary physics, a world spinning near the edge of structural stability, a planet whose very shape has been molded by rotation, and perhaps a planet that is slowly losing pieces of itself to space. But Haumea also teaches us something important about planetary formation. In the early solar system, collisions and gravitational interactions were far more common than they are today. Planets, dwarf planets, and large asteroids frequently struck one another. Some worlds were shattered completely, others merged together, and some, like Haumea, survived catastrophic impacts but were forever changed by them. The rapid rotation we observe today may be a direct consequence of that ancient violence, a reminder that the solar system's history was not peaceful. It was chaotic, dynamic, and often destructive. Yet from that chaos emerged the complex planetary system we see today, including one strange, elongated dwarf planet spinning quietly in the darkness beyond Neptune. A world that rotates faster than almost any other planetary body we know. A planet that has been stretched, reshaped, and perhaps even slowly eroded by its own motion. And yet, despite all of this, Haumea continues spinning, hour after hour, year after year, completing another rotation every 4 hours. A silent cosmic dance that has continued for billions of years. But perhaps the most fascinating question still remains. If Haumea is already spinning near its maximum possible speed, what would happen if something nudged it just a little faster? Would the planet begin to break apart? Would new rings form around it? Or could an entirely new family of icy worlds emerge, born from fragments of a spinning dwarf planet pushed beyond the limits of stability? In the next part, we will explore the moons of Haumea. Because these two small companions may hold crucial clues about the dwarf planet's violent past and the dramatic collision that created the fastest spinning world in the solar system. Far beyond the orbit of Neptune, where sunlight fades into a faint blue glow, the strange dwarf planet Haumea is not alone. Two small worlds orbit this spinning body. They are tiny compared to planets, but their existence may hold the key to understand it, one of the most violent events in the history of the outer solar system. These moons are called Hiʻiaka and Namaka. At first glance, they might seem like ordinary satellites. Many planets have moons after all. Even small asteroids sometimes have companions. But the moons of Haumea are different. They carry the fingerprints of a catastrophic collision that occurred billions of years ago. A collision powerful enough to reshape an entire world. The discovery of Haumea's moons. The first of Haumea's moons, Hiʻiaka, was discovered in 2005 using the powerful W.M. Keck Observatory. Astronomers were already studying Haumea's brightness variations when they noticed something unusual. Near the dwarf planet, a faint object was moving along with it. Further observations confirmed that this was not a distant star. It was a moon. Soon after, a second, smaller moon was discovered closer to Haumea. This object would later be named Namaka. Together, these two moons formed a miniature planetary system orbiting a rapidly spinning dwarf planet. But their significance went far beyond their existence. Their composition revealed something extraordinary. Moons, made of ice. Spectroscopic observations of both moons showed that their surfaces are dominated by water ice. That alone is not particularly surprising in the distant outer solar system. But what made scientists take notice was how pure the ice appeared to be. Most objects in the Kuiper Belt contain a mixture of materials. Their surfaces often include dark organic compounds, methane ice, nitrogen ice, and complex chemical residues produced by cosmic radiation. Yet Hiʻiaka and Namaka looked unusually bright and reflective. Their surfaces seemed to contain mostly water ice. This composition closely matches the surface of Haumea itself. Such similarity strongly suggests that the moons and the dwarf planet share a common origin. They were likely born from the same event, an ancient impact. The collision that created a system. Billions of years ago, Haumea may have been struck by another large Kuiper Belt object. The collision was probably not a direct head-on impact. Instead, scientists believe it may have been a glancing blow, a massive body scraping across the outer layers of Haumea. The impact would have been devastating. Huge amounts of icy material would have been blasted into space, fragments ranging from tiny particles to large chunks hundreds of kilometers across. Some of this debris escaped Haumea's gravity entirely. Those fragments became the objects we now call the Haumea family, a group of icy bodies sharing similar orbits in the Kuiper Belt. But not all of the debris escaped. Some pieces remained trapped by Haumea's gravity. Over time, those fragments began orbiting the dwarf planet. Slowly, gravity gathered them together. Small clumps collided and merged. Eventually, two larger bodies emerged. These bodies became the moons, Hiʻiaka and Namaka. In other words, Haumea's moons may be made from pieces of the dwarf planet itself, fragments torn away during one of the most violent events in the solar system's history. The outer moon, Hiʻiaka. Hiʻiaka is the larger of the two moons. With a diameter of about 310 kilometers, it is still tiny compared to most planetary satellites, but large enough to form a nearly spherical shape. Hiʻiaka orbits Haumea at a distance of about 49,000 kilometers. It takes roughly 49 days to complete one orbit. From Haumea's surface, Hiʻiaka would appear as a small but bright object moving slowly across the sky. Because Haumea rotates every 4 hours, the moon's motion across the sky would look unusual. The dwarf planet would spin rapidly beneath it, creating constantly changing perspectives. Hiʻiaka's surface appears to be coated in crystalline water ice. This kind of ice usually forms when water molecules arrange themselves into an ordered structure. But there is a mystery here. Crystalline ice normally requires some form of heating to form. Yet the Kuiper Belt is extremely cold. Temperatures there can fall below minus 220 degrees Celsius. Under such conditions, crystalline ice should gradually degrade into amorphous ice due to radiation from cosmic rays. The fact that Hiʻiaka still shows crystalline ice suggests something interesting. Either the ice is relatively young, or some process is refreshing the surface. One possibility is that the ancient collision that created the Haumea system also heated the debris enough to crystallize the ice. Another possibility is that impacts from micrometeorites occasionally expose fresh ice beneath the surface. For now, scientists are still investigating. The inner moon, Namaka, the smaller moon, Namaka, presents an even more complicated picture. Namaka is roughly 170 kilometers in diameter. It orbits much closer to Haumea than Hiʻiaka does. And because of this proximity, Namaka experiences stronger gravitational interactions. Its orbit is more irregular and more dynamic. In fact, the two moons interact with each other gravitationally. Their orbits slowly shift and change over time. These interactions create a fascinating gravitational dance around Haumea. By carefully studying the motions of Hiʻiaka and Namaka, astronomers have been able to calculate Haumea's mass. Despite its large size, Haumea's mass is relatively low compared to some other dwarf planets. This supports the theory that much of its original mass was lost during the ancient collision. Haumea may once have been a significantly larger world, but the impact stripped away large portions of its icy mantle. What remains today may be only the surviving core. A frozen family. The existence of Haumea's moons, combined with the scattered fragments of the Haumea family, provides one of the clearest examples of a collisional family in the outer solar system. Such families are common in the asteroid belt between Mars and Jupiter, but in the Kuiper Belt, they are much harder to detect. The region is vast, and objects are extremely distant. Yet Haumea stands out. Its family members share distinctive properties, similar orbits, similar compositions, and surfaces dominated by water ice, all signs pointing toward a common origin, a shattered world whose fragments still drift through space billions of years later. What the moons reveal about Haumea. The moons of Haumea are more than just companions. They are evidence. Evidence of a dramatic event that reshaped an entire planetary system. Without Hiʻiaka and Namaka, scientists might never have realized how violent Haumea's past truly was. The moons tell us that Haumea did not simply form quietly in the outer solar system. It survived something catastrophic, a collision powerful enough to tear away much of its outer layers. A collision that may also explain why Haumea spins so incredibly fast today. But the story may not be finished, because the Haumea system still contains one more strange feature, a feature that scientists did not discover until 2017. A thin ring of icy particles orbiting the dwarf planet. Rings are common around giant planets like Saturn. But around a small dwarf planet like Haumea, that was completely unexpected. The ring may contain debris from the ancient collision, or it may have formed from particles slowly escaping Haumea's equator due to its rapid rotation. Either way, it adds yet another layer of mystery to this already strange world. Because Haumea is not just a rapidly spinning dwarf planet with two moons. It is an entire miniature system shaped by a violent past, a frozen relic of planetary destruction. And as we move deeper into the Kuiper Belt in our exploration, we may eventually discover that Haumea is only the beginning. a glimpse into a hidden history of collisions, fragments, and spinning worlds waiting to be discovered at the far edge of our solar system. In the next part, we will explore Haumea's mysterious ring and why its existence surprised astronomers around the world. For most of human history, planetary rings were thought to belong only to the giants of our solar system. When Saturn revealed its spectacular rings through early telescopes, astronomers assumed such structures required enormous gravitational forces to exist. Later discoveries confirmed that Jupiter, Uranus, and Neptune also possessed rings. But these were all massive gas giants, worlds with powerful gravity capable of trapping enormous clouds of orbiting debris. Small planetary bodies were never expected to have rings. Yet once again, Haumea refused to follow the rules. In 2017, astronomers made a discovery that completely changed how scientists think about rings in the solar system. Haumea, a distant dwarf planet more than 6 billion kilometers from the Sun, was found to possess its own ring system, and no one had predicted it. How the ring was discovered. Unlike planets closer to Earth, Haumea is far too distant to photograph clearly with most telescopes. Even the most powerful observatories see it as little more than a tiny point of light. So, astronomers often rely on clever techniques to study objects that cannot be directly imaged. One of these techniques is called stellar occultation. An occultation occurs when a distant object passes in front of a star. For a brief moment, the star's light disappears. By measuring exactly when the starlight fades and reappears, scientists can determine the size and shape of the object blocking the light. In January 2017, astronomers around the world prepared for such an event. Haumea was predicted to pass directly in front of a distant star. Telescopes across several continents were pointed toward the sky, waiting for the moment when the star would vanish behind the dwarf planet. When the event finally occurred, something unexpected appeared in the data. The star dimmed before Haumea actually blocked it. Then the light returned briefly, and then it disappeared again as the dwarf planet passed in front of it. After Haumea moved away, the same pattern occurred in reverse. A slight dimming, a brief return of starlight, then complete darkness. This pattern puzzled astronomers. It suggested that something thin and circular was orbiting the dwarf planet, something large enough to block a small portion of the starlight before and after Haumea itself passed by. Further analysis revealed the answer. Haumea had a ring, a thin halo of ice. The ring around Haumea is not enormous like Saturn's. In fact, it is extremely thin. It lies roughly 2,300 kilometers from the center of the dwarf planet, orbiting very close to the equatorial plane. Its width is only about 70 kilometers, and its particles are likely composed of small fragments of water ice. Compared to the bright rings of Saturn, Haumea's ring is faint and subtle, but its existence is still remarkable because Haumea is only a dwarf planet. Its gravity is far weaker than that of the gas giants. For a long time, scientists assumed that objects this small could not maintain stable rings, yet Haumea clearly does. This discovery forced astronomers to rethink how ring systems form and survive. Why the ring is so strange. The most surprising aspect of Haumea's ring is its location. the ring orbits at almost exactly the same rate as Haumea's rotation. In other words, the particles in the ring take roughly 4 hours to complete an orbit around the dwarf planet. That is the same amount of time Haumea takes to spin once. This means the ring lies near what scientists call a resonant orbit. At this distance, the gravitational and rotational forces of the dwarf planet interact in a very specific way. The particles remain locked in a stable configuration. It is almost as if the ring is synchronized with Haumea's rotation. And that raises an intriguing possibility. The ring may actually be connected to the dwarf planet's extreme spin. A ring born from rotation. Remember that Haumea is spinning very close to its theoretical breakup speed. Centrifugal forces are extremely strong near the equator. Some scientists believe that small fragments of ice may occasionally break loose from the surface. Once those fragments escape the surface, they could enter orbit around the dwarf planet. Over time, many such fragments could gather together, forming a thin ring. In this scenario, the ring would not be the result of a single dramatic event. Instead, it would slowly grow over millions of years as Haumea sheds tiny pieces of itself. This process would be subtle, a slow leaking of material from the equator of a rapidly spinning world. And because the fragments originate near the equator, they would naturally settle into a ring aligned with Haumea's rotation. But there is another possible explanation, a remnant of the ancient collision. Some astronomers think the ring may be leftover debris from the same ancient collision that created Haumea's moons. When that catastrophic impact occurred billions of years ago, enormous amounts of ice were thrown into space. Much of the debris escaped entirely. Some pieces eventually formed the moons Hiʻiaka and Namaka, but smaller fragments may have remained trapped in orbit around the dwarf planet. Over billions of years, gravitational interactions could have gradually concentrated those particles into a narrow ring. If this theory is correct, the ring is not something Haumea is producing today. Instead, it is a fossil, a remnant of the ancient impact that reshaped the dwarf planet long ago. Either way, the ring provides an extraordinary glimpse into Haumea's past. Rings around, small worlds. Haumea's ring is not entirely unique. In recent years, astronomers have discovered rings around a few other small bodies. One example is Chariklo, a relatively small object orbiting between Saturn and Uranus. Another object, called Chiron, may also possess ring-like structures. These discoveries have forced scientists to rethink how rings form. It now appears that rings may be more common than previously believed. Even small bodies with relatively weak gravity may be able to maintain narrow rings under the right conditions. Haumea simply represents one of the most dramatic examples. A delicate structure. Despite its stability today, Haumea's ring is fragile. Tiny particles orbiting a small dwarf planet are constantly influenced by many forces. Gravitational interactions with the moons, radiation pressure from sunlight, micrometeorite impacts. Over long timescales, these processes could slowly disperse the ring. Particles might drift inward and eventually fall onto Haumea's surface. Others might escape the dwarf planet's gravity entirely. The ring may therefore be temporary on cosmic timescales. It could disappear millions of years from now, or it could evolve into something entirely different. perhaps even forming a new moon. For now, however, the ring remains intact, a thin halo of ice surrounding one of the most unusual worlds in the solar system. A system shaped by chaos. When we step back and look at the entire Haumea system, the picture becomes clear. This is not just a dwarf planet. It is an entire miniature planetary system, a rapidly spinning central world, 2 icy moons, a narrow ring, and a scattered family of fragments drifting through the Kuiper Belt. All of these pieces tell the story of a single violent event, a collision that occurred billions of years ago, a moment when 2 worlds struck each other in the darkness beyond Neptune. The aftermath of that collision still exists today, frozen, silent, and slowly evolving. Yet despite everything astronomers have learned about Haumea, one mystery still remains. The dwarf planet's surface is incredibly bright, far brighter than most objects in the Kuiper Belt. Why? What keeps its icy surface so reflective after billions of years of exposure to cosmic radiation? Is the surface being refreshed somehow? Or are we seeing the exposed interior of a shattered world? In the next part, we will explore Haumea's strange and brilliant surface and what it reveals about the hidden processes shaping this distant spinning world. Far beyond the orbit of Neptune, sunlight becomes incredibly weak. At the distance of Haumea, the sun appears more like a brilliant star than the blazing disk we see from Earth. It provides only a tiny fraction of the warmth and light that reaches the inner solar system. Yet despite this dim environment, Haumea shines surprisingly brightly. When astronomers measure the amount of sunlight reflecting from the dwarf planet, they find something unusual. Haumea reflects a large portion of the light that hits it, much more than most objects in the Kuiper Belt. In fact, Haumea is one of the most reflective large bodies ever discovered in the outer solar system. This property is known as albedo, the fraction of incoming light that a surface reflects. A dark object has a low albedo. A bright, icy surface has a high one. Haumea's albedo is extremely high, suggesting that its surface is covered in fresh, clean ice. But that creates a mystery, because over billions of years, radiation should have darkened that surface. The problem with space ice. The outer solar system may look quiet and frozen, but it is actually a hostile environment. Cosmic rays constantly bombard distant objects. High-energy particles from the sun and deep space slowly alter the chemistry of exposed surfaces. When this radiation strikes ice mixed with organic molecules, it triggers chemical reactions. Over time, the surface becomes darker and redder. This process has affected many Kuiper Belt objects. For example, the dwarf planet Pluto has regions covered in reddish compounds called tholins, complex organic molecules created by radiation interacting with methane and nitrogen ice. These substances slowly accumulate over millions of years. If Haumea had remained untouched since the early solar system, its surface should look much darker today. Yet observations show the opposite. Its surface appears dominated by bright water ice. Something must be keeping that surface clean. But what? Crystalline ice in a frozen world. Another clue comes from the structure of the ice itself. Water ice can exist in different forms depending on temperature and radiation exposure. One of these forms is called crystalline ice. In crystalline ice, water molecules arrange themselves in an orderly structure. This type of ice forms when water freezes slowly or when ice experiences some heating. But there is another form called amorphous ice. In amorphous ice, the molecules are arranged randomly. Radiation gradually converts crystalline ice into amorphous ice over time. Because of this, scientists expected that distant objects in the Kuiper Belt would mostly contain amorphous ice. Yet spectroscopic studies of Haumea revealed something surprising. Its surface appears dominated by crystalline water ice. This suggests that the ice was heated at some point in the past. But where could that heat have come from in such a cold region of space? The heat of an ancient collision. One possible explanation goes back to the violent impact that may have created the Haumea system. When a massive collision occurs between planetary bodies, enormous amounts of energy are released. The impact can melt ice and rock instantly. For a brief time, parts of the surface may even become liquid before rapidly freezing again. If Haumea experienced such a collision billions of years ago, the impact could have melted much of its icy mantle. When the surface cooled again, the ice would have crystallized. This would explain why Haumea and many members of the Haumea family share similar water-ice signatures. But there is still a problem with this explanation. Radiation should gradually destroy crystalline ice over tens of millions of years. Yet Haumea's surface remains crystalline today. That means something may still be refreshing the surface. A surface that changes. One possibility is that Haumea's rapid rotation plays a role. Remember that the dwarf planet spins once every 4 hours. That speed creates powerful stresses within the icy crust. Over long periods of time, these stresses could produce fractures across the surface. Large sections of ice might shift or slide. Fresh ice buried beneath the surface could occasionally be exposed. These slow geological processes might help maintain Haumea's bright appearance. Another possibility involves impacts from small objects. Even in the distant Kuiper Belt, collisions still occur. Small meteoroids occasionally strike the surfaces of dwarf planets and moons. When they do, they can excavate fresh material from beneath the surface. These impacts might periodically reveal new layers of ice. Over time, a series of tiny collisions could slowly refresh the surface. Could Haumea have ice volcanoes? Some scientists have proposed an even more intriguing possibility. What if Haumea once had cryovolcanoes? Cryovolcanoes are icy volcanoes that erupt water, ammonia, or other volatile materials instead of molten rock. They exist in several places in the outer solar system. For example, the moon Enceladus ejects plumes of water vapor into space from cracks near its south pole. Another moon, Europa, may also experience cryovolcanic activity. If Haumea once contained internal heat, perhaps from radioactive elements in its rocky core, it might have produced similar eruptions in the distant past. These eruptions could have resurfaced parts of the dwarf planet with fresh ice. Although Haumea is likely inactive today, remnants of those processes might still exist in its surface composition. The dark spot on Haumea. Despite its overall brightness, Haumea is not perfectly uniform. Astronomers studying variations in its reflected light have identified a darker region on its surface. This region rotates into view periodically as the planet spins. it appears slightly redder and darker than the surrounding ice. Scientists sometimes refer to this feature as the dark red spot. The nature of this region remains uncertain. It could be an area where radiation has darkened the ice more heavily, or it might be the site of an ancient impact. Some researchers even speculate that it could mark a location where subsurface material was exposed during the collision that created the Haumea system. Whatever its origin, the dark spot adds another layer of complexity to this already unusual world. A world that reflects its past. When we examine Haumea's surface, we are not just seeing frozen ice. We are seeing the aftermath of billions of years of cosmic history. The bright ice tells us that the surface has been refreshed. The crystalline structure suggests heating events in the past. The darker regions hint at impacts or chemical alterations. Every feature is a clue, a piece of a puzzle that scientists are still trying to assemble. Yet despite the enormous distance between Haumea and Earth, we have already learned a remarkable amount about this strange dwarf planet. We know that it spins faster than almost any other world of its size. We know that it is elongated rather than spherical. We know it has two moons, Hiʻiaka and Namaka, and we know that a thin ring of icy particles circles its equator. But perhaps the most remarkable thing about Haumea is that it survived. It survived a catastrophic collision. It survived billions of years of radiation and impacts, and it continues spinning rapidly in the darkness beyond Neptune. A frozen relic of the chaotic early solar system. Yet even now, one final mystery remains. Haumea rotates incredibly fast, so fast that it sits near the theoretical limit where a planetary body could begin to tear itself apart. What would happen if its rotation increased just a little more? Could Haumea eventually break apart and create a new family of icy worlds in the Kuiper Belt? In the next part, we will explore the ultimate limits of planetary rotation and what the future might hold for the fastest spinning world in our solar system. In the cold darkness of the outer solar system, the dwarf planet Haumea continues its relentless spin. Every 4 hours, it completes another rotation, hour after hour, year after year, for billions of years. But this rapid motion raises a fascinating possibility. Haumea may be spinning dangerously close to the limit of stability, a limit beyond which a world can no longer hold itself together, a limit where gravity begins to lose its battle against rotation. And if that limit is ever crossed, the planet could begin to change dramatically. The tipping point of rotation. Every rotating object in the universe experiences centrifugal force. This force pushes material outward from the center of rotation. On a slowly rotating planet like Earth, this force is relatively weak. Gravity easily overpowers it, keeping the surface stable. But as rotation increases, centrifugal force grows stronger. At some point, it begins to compete directly with gravity, and eventually, a critical threshold can be reached. At this threshold, known as the breakup speed, centrifugal force at the equator equals the gravitational force pulling material inward. If a planet spins faster than this limit, particles on the surface could begin to lift away. The world would slowly start losing pieces of itself. In extreme cases, the entire object might fragment. Fortunately, Most planets spin far below this limit, but Haumea is different because it rotates once every 4 hours. It may already be close to the maximum speed that an icy dwarf planet of its size can survive. Some models suggest that if Haumea rotated even a little faster, its equatorial regions could begin shedding material into space. What would breaking apart look like? If Haumea were pushed beyond its rotational stability limit, the first changes would likely appear at the equator. The equator is where centrifugal forces are strongest. Small pieces of ice might begin to loosen. Fragments could slowly drift away from the surface. Instead of falling back down, these fragments could enter orbit around the dwarf planet. Over time, they might form a ring. Interestingly, Haumea already has one, a thin ring of icy particles discovered in 2017. Some scientists believe this ring may already represent material that escaped from the dwarf planet. If that idea is correct, Haumea may already be experiencing the earliest stages of rotational mass loss, but the process would likely be slow. Instead of dramatic explosions, the dwarf planet might gradually shed tiny fragments over millions of years. These fragments could accumulate in orbit, forming new rings or even small moons. In effect, Haumea might slowly create its own miniature planetary system. Could Haumea ever fully break apart? While Haumea rotates extremely fast, it is unlikely to suddenly shatter. Gravity still holds the planet together, and the dwarf planet's structure may already be adjusted to its extreme rotation. Over billions of years, its internal layers have likely redistributed themselves to maintain stability. The icy mantle has stretched. The rocky core remains dense enough to anchor the structure. Together, they maintain the delicate balance between gravity and centrifugal force. However, future events could still alter this balance. For example, a large impact could change Haumea's rotation. If another Kuiper Belt object struck the dwarf planet at the right angle, it could increase the spin slightly. Even a small change might push the planet closer to the instability limit. But collisions in the Kuiper Belt are rare today. The region is vast and objects are widely spaced. The violent chaos of the early solar system has largely faded, so for now, Haumea is likely to continue spinning in relative stability. A cosmic balancing act. The physics of Haumea is a remarkable example of balance in the universe. Gravity pulls inward, rotation pushes outward. For billions of years, those forces have remained in equilibrium. But this equilibrium produces one of the most unusual worlds we know. A dwarf planet stretched into an elongated shape. A planet spinning faster than almost any other object of comparable size. A planet surrounded by a ring and 2 small moons, Hiʻiaka and Namaka. Together, these features make Haumea one of the most fascinating objects in the solar system. But the dwarf planet also teaches scientists something important. Planetary bodies are not always static. They evolve, they collide, they reshape themselves under extreme forces. Haumea is a reminder that even frozen worlds billions of kilometers away can have violent and dynamic histories. Could Haumea form more moons? If Haumea continues losing small amounts of material from its equator, it might slowly build additional rings or moons. Tiny fragments escaping from the surface could collide with one another. Some pieces might merge together. Over immense periods of time, these fragments could grow into small satellites. This process is thought to have occurred around other planets as well. For example, the rings of Saturn contain countless particles ranging from dust grains to large chunks of ice. In some cases, small moonlets form within those rings. If similar processes occur around Haumea, the dwarf planet might eventually develop additional moons, a slowly evolving system shaped by its extreme rotation. The long future of Haumea. The future of Haumea will likely unfold over unimaginable timescales. Millions of years from now, its rotation may slowly decrease as gravitational interactions with its moons subtly drain angular momentum. Alternatively, the ring might disperse. Particles could drift inward and fall back onto the surface. Others might escape entirely. Eventually, the system may stabilize into a slightly slower rotation. But even then, Haumea will remain an extraordinary object, a survivor of an ancient collision, a planet stretched by its own motion, and one of the fastest spinning large bodies in the solar system. Yet despite everything scientists have learned about this distant world, one fact remains clear. We have never seen Haumea up close. All of our knowledge comes from telescopes observing a faint point of light billions of kilometers away. Imagine what we might discover if a spacecraft someday traveled to this strange dwarf planet. We could see its elongated shape directly. We could study its icy surface in detail. We could explore its moons and ring system, and we might finally understand how such a bizarre world came to exist. For now, however, Haumea remains distant, a spinning silhouette at the edge of the solar system. A reminder that even in the coldest and darkest regions of space, nature can create worlds that challenge everything we thought we knew about planets. And in the final part of this journey, we will step back and look at the bigger picture. Because Haumea is more than just a strange dwarf planet, it is a window into the chaotic history of the solar system itself, a story of collisions, survival, and the incredible forces that shape the worlds around us. At the far edge of our solar system, more than 6 billion kilometers from the Sun, a strange frozen world continues its endless rotation. That world is Haumea. It spins once every 4 hours, not because something is pushing it, not because something is forcing it, but because billions of years ago, something happened that permanently changed its fate. A collision, a moment of chaos that reshaped a world and left behind one of the most unusual planetary bodies ever discovered. And today, as it quietly circles the Sun once every 285 years, Haumea remains a frozen witness to the violent past of the solar system. A planet that should not exist. Like this, when astronomers first discovered Haumea, they expected to find another ordinary dwarf planet, perhaps something similar to Pluto or Eris, a cold spherical world drifting silently through the darkness beyond Neptune. Instead, they found something completely different, a planet stretched into an elongated shape, a body spinning faster than almost any other planetary object in the solar system, a world surrounded by a ring and 2 moons, and perhaps most remarkably of all, a dwarf planet that sits near the physical limit of rotational stability. Haumea challenges our understanding of how planets form and evolve, because in many ways it behaves less like a stable planet and more like the surviving fragment of a much larger world, the survivor of a cosmic catastrophe. The evidence suggests that Haumea's unusual properties all trace back to a single event, a massive collision that occurred billions of years ago in the distant Kuiper Belt. At that time, the outer solar system was still crowded with icy worlds. Their orbits were unstable, their paths crossed, and when they collided, the impacts could be catastrophic. One such impact may have struck the original Haumea. The collision likely ripped away large portions of its icy mantle. Fragments were blasted into space. Some of those fragments eventually formed the moons Hiʻiaka and Namaka. Others became the scattered members of the Haumea family, a group of icy bodies that still share similar orbits today. But the central core survived. And because of the physics of angular momentum, the surviving remnant began spinning faster and faster. Over time, that rapid rotation stretched the dwarf planet into the elongated shape we see today. Haumea is therefore not simply a dwarf planet. It may be the exposed core of a once larger world. A system born from violence. The entire Haumea system tells the story of that ancient catastrophe. The moons are fragments that never escape the dwarf planet's gravity. The ring may contain debris left over from the same event. And the scattered icy objects drifting through the Kuiper Belt may be distant relatives, remnants of the shattered world. In many ways, Haumea resembles a miniature planetary system born from destruction, a central body spinning rapidly, two small satellites orbiting nearby, a thin ring circling its equator, all of it shaped by a single moment of violent impact billions of years ago. A planet at the edge of physics. Perhaps the most fascinating aspect of Haumea is how close it may be to the limits of planetary stability. If a planet spins too slowly, gravity simply keeps it round. But if it spins too quickly, centrifugal forces begin to tear it apart. Haumea exists somewhere between those extremes. It spins so rapidly that its shape has been permanently distorted. Yet gravity still holds it together. This delicate balance makes Haumea one of the most extreme natural experiments in planetary physics. It shows us what happens when a world rotates near its structural limit. And it raises a fascinating possibility. If Haumea spun just a little faster, it might begin losing pieces of itself. Fragments of ice might escape from the equator. New rings could form, perhaps even new moons. In other words, Haumea might slowly evolve into something entirely different. Why Haumea matters. At first glance, Haumea might seem like just another distant dwarf planet, but studying it helps scientists answer much larger questions about our solar system. For example, how common are catastrophic planetary collisions? How do planets respond when their rotation approaches extreme speeds? How do rings and moons form around small bodies? And how do planetary systems evolve after violent events? Haumea provides clues to all of these questions. It offers a glimpse into the chaotic early history of our solar system, a time when planets were still forming, when collisions were common, and when worlds were constantly reshaped by gravity and impact. Today, the solar system appears relatively calm, but objects like Haumea remind us that the past was far more turbulent. A world we have never seen. Despite everything scientists have learned about Haumea, one fact remains remarkable. No spacecraft has ever visited it. All of our knowledge comes from telescopes observing a tiny point of light billions of kilometers away. From that faint signal, astronomers have deduced its rotation, its shape, its moons, its ring, and even the composition of its icy surface. Imagine what we might discover if a spacecraft someday traveled to this distant world. We could see Haumea's elongated shape directly. We could map its icy surface. We could fly through its ring. We could study the moon's Hiʻiaka and Namaka up close. And we might finally uncover the full story of the ancient collision that created this extraordinary system. But such a mission would take decades. For now, Haumea remains a distant mystery, a rapidly spinning world hidden in the darkness beyond Neptune. The endless spin. And yet, while we observe from afar, Haumea continues its silent rotation. Every 4 hours, it completes another spin. The sun rises and sets rapidly across its icy surface. Its moons circle slowly through the cold sky. Tiny particles in its ring glide endlessly around the equator. Nothing changes quickly in the outer solar system. But over billions of years, even small forces can reshape entire worlds. Perhaps one day Haumea will spin slightly slower. Perhaps its ring will disperse. Perhaps new fragments will escape its surface. Or perhaps it will remain almost exactly as it is today, a frozen relic of a violent past, a distant world shaped by collision, rotation, and survival. A reminder of the solar system's violent origins. When we look at the solar system today, it can appear calm and orderly. The planets move along predictable paths. Moons orbit quietly around their worlds. Everything seems stable. But objects like Haumea reveal a deeper truth. The solar system was not always peaceful. It was once a place of constant collisions and dramatic transformations. Worlds were shattered, fragments were scattered across space, and from that chaos emerged the planetary system we see today. Haumea is one of the survivors of that era, a spinning remnant of a world that was nearly destroyed, a frozen record of an ancient cosmic disaster, and one of the strangest planets ever discovered. Because sometimes the most fascinating worlds in the universe are not the ones that formed perfectly. They are the ones that survived far beyond the familiar planets of the inner solar system, past the orbit of Neptune, where sunlight fades into a distant glow. A strange, frozen world continues its silent motion. That world is Haumea. It spins once every 4 hours, faster than almost any other planetary body we know. Its shape is stretched and distorted, more like a cosmic football than a sphere. 2 small moons orbit nearby. A faint ring of debris circles its equator, and all of it drifts through one of the coldest regions of our solar system. But Haumea is more than just another distant object. It is a survivor. To understand why Haumea looks the way it does today, we have to go back billions of years, to a time when the solar system was far more chaotic than it is now. The solar system was once a violent place. Today, the solar system appears calm and orderly. The planets follow stable orbits. Moons circle their worlds quietly. Asteroids and comets move along predictable paths. But the early solar system was nothing like this. After the Sun formed about 4.6 billion years ago, countless rocky and icy bodies were left orbiting the newborn star. These objects collided constantly. Some merged to form planets, others shattered into fragments. In those early ages, worlds were not permanent. They were fragile. A single collision could reshape an entire planet. And somewhere in the distant region beyond Neptune, one such collision changed Haumea forever. The impact that reshaped a world. Scientists believe that Haumea was once very different. It may have been a much larger object, possibly closer to a typical dwarf planet like Pluto or Eris. But then something happened. Another large icy body slammed into it. The collision would have been unimaginably violent. The impact likely stripped away large portions of Haumea's outer layers, blasting ice and debris into space. Fragments scattered throughout the surrounding region, forming what scientists now call the Haumea family, a group of icy objects that share similar orbits and compositions. Some of those fragments never escaped Haumea's gravity. Instead, they became its moons. Today, we know them as Hiʻiaka and Namaka, and the rest of the debris may have eventually formed the faint ring that circles the dwarf planet. But perhaps the most dramatic result of this ancient collision was something else entirely. Haumea began spinning, faster and faster. A planet, spinning near its limit. When a collision transfers angular momentum to a planetary body, it can dramatically increase the planet's rotation speed. That is exactly what appears to have happened to Haumea. Today, the dwarf planet rotates once every about 3.9 hours. For comparison, Earth rotates once every 24 hours. Jupiter, the fastest spinning planet, rotates every about 10 hours. Yet Haumea, far smaller than those worlds, spins much faster. This incredible rotation speed stretches the planet outward along its equator. Instead of forming a sphere, Haumea has become elongated. Its shape resembles a spinning rugby ball or oval. Gravity still holds the planet together, but only barely. Scientists believe Haumea is rotating close to the limit at which a planetary body can remain intact. If it spun much faster, parts of its icy surface might begin breaking away. And if that happened, Haumea could eventually create new rings or moons. A world made of ice. Another unusual feature of Haumea is its surface. Spectroscopic observations show that the dwarf planet is covered almost entirely in crystalline water ice. This ice reflects sunlight extremely well, making Haumea one of the brightest objects in the Kuiper Belt. But that brightness raises an interesting question. Water ice exposed to cosmic radiation should gradually darken over millions of years. Yet Haumea's surface appears surprisingly fresh. This suggests that something may be renewing the surface, possibly internal processes, or the exposure of deeper layers of ice during the ancient collision. If that is true, Haumea might still be slowly evolving even today. The Haumea system. The dwarf planet is not alone. Orbiting Haumea are two small moons. Hiʻiaka, the larger of the two, orbits farther out and appears to be composed mostly of water ice. Namaka, the smaller moon, follows a closer orbit and experiences strong gravitational interactions with both Haumea and its sibling moon. Together, these moons help astronomers understand the mass and gravitational influence of the dwarf planet. And then there is the ring. For many years, scientists believed rings were found only around giant planets like Saturn. But in 2017, astronomers discovered that Haumea also possesses a thin ring made of icy particles. The ring orbits near the dwarf planet's equator, the region where its rapid rotation has stretched the planet the most. Its origin is still debated. Some scientists believe the ring formed from debris created during the ancient collision. Others suggest it could be material gradually escaping from the planet's surface. Either way, it makes Haumea one of the most unusual dwarf planets ever discovered. A window into the past. Objects, like Haumea, are important, not just because they are strange. They are important because they preserve clues about the early solar system. The distant region where Haumea lives, known as the Kuiper Belt, contains thousands of frozen relics from the time when planets were forming. Unlike the inner solar system, where collisions and solar radiation have heavily altered planetary surfaces, the Kuiper Belt remains relatively unchanged. Many of its objects are ancient. Some may have remained almost exactly the same for billions of years. By studying Haumea and similar bodies, scientists can learn about the conditions that existed during the earliest stages of planetary formation. A destination for future exploration. Despite everything we have learned about Haumea, there is one important fact to remember. No spacecraft has ever visited it. All of our knowledge comes from telescopes observing a tiny point of light billions of kilometers away. Imagine what we might discover if a mission traveled to Haumea. A spacecraft could map its elongated shape in detail. It could explore the ring system. It could examine the surfaces of Hiʻiaka and Namaka. It could study the crystalline ice covering the dwarf planet. And perhaps most importantly, it could help confirm the story of the ancient collision that shaped this strange world. But reaching Haumea would not be easy. At its current distance, a spacecraft might take 20 or 30 years to arrive. For now, Haumea remains a distant mystery. A silent world at the edge of the sun's influence. Out in the dark frontier of the solar system, the sun appears only as a bright star. Temperatures plunge to unimaginable lows, and worlds like Haumea drift slowly through the cosmic darkness. Yet even here, far from the warmth of the sun, the history of the solar system is written into the shapes and motions of distant planets. Haumea is one of those records, a world stretched by rotation, a survivor of a catastrophic collision, a frozen remnant of the violent age when planets were still forming. And as it continues its endless spin in the distant Kuiper Belt, it reminds us of something extraordinary. Even in the coldest and most remote corners of our solar system, the story of creation and destruction is still written across the stars.